Hello Chem 1A, this is chapter 3, lecture video 11, and this is our last lecture video for this chapter. In this, we're going to be talking about combustion reactions and specifically combustion analysis, which is another way to determine molecular and empirical formulas using a technique of basically blowing up the unknown compound. So what is a combustion reaction? Combustion reactions are probably one of the most important reactions that we currently use today. We pretty much use it for almost everything, from anything like an oil power plant or a coal power plant or your car, unless you have like a Tesla, in which case I'm totally jealous. That uses a different type of reaction. But we use combustion reactions for a lot of our energy needs and electricity needs. So it's the result of burning a fuel. This reaction generally releases quite a bit of heat. It's very exothermic, which is a reaction that releases heat. This gives us energy. Heat is a form of energy. That energy allows us to do work like moving your car forward or powering a house or any other type of work that we'd like to do. Most combustion reactions, oxygen is one of the reactants, and the other one is a fuel, right? So like an organic compound reacting with oxygen is a combustion reaction for sure. When we react oxygen with an organic compound containing carbon, hydrogen, and oxygen, we're always going to get the same products, and those products are going to be carbon dioxide, in other words, CO2, and water, H2O. So these products are going to be what we see in a combustion reaction, and we need to know that for when we're talking about combustion chemical analysis. So if I'm doing a combustion analysis, I have some unknown compound here. I've put it in what we call a blast furnace, and what this is it's just like a souped up oven, right? Not an oven that goes to 500 Fahrenheit like your oven at home, but one that can go up to a couple thousand degrees Celsius. And so we're going to basically just heat up this solid until it reaches what's known as its flash point. Basically the temperature that it will combust with oxygen. We have oxygen flowing through this container. Once it explodes and it combusts, it's going to form H2O and CO2. And we're going to have containers down the way that absorb water and absorb carbon dioxide. Now what we can do is we can measure the mass of this absorber before the combustion reaction and after, and the change in the mass is how much water was produced by our reaction. The same thing for our CO2 absorber. We measure the mass before and then after, and the mass is going to go up. This will allow us to measure how much CO2 in grams was produced by this chemical reaction. This allows us to actually back calculate what the empirical formula of the unknown compound is, or in many cases, if we know the molar mass, then we can also determine the molecular formula. So just down here, what we're talking about is that, hydrocarbons, when we combust them, they're going to burn CO2, form CO2 and water. One of the things that's very important here is where all this hydrogen came from in the water. It only could have come from one place, our organic compound that's the unknown, right? Because oxygen doesn't contain any hydrogen. The same thing is true of the carbon in CO2. All the carbon in CO2 had to come from our unknown. We can use this relationship to figure out how many moles of carbon and moles of hydrogen were originally present in the unknown compound. Then, once we have moles of both, we can determine the empirical formula. So let's do an example of that in a second. There is a small hiccup if our unknown compound contains oxygen. If our unknown compound contains oxygen, things get a little bit tricky. And this is because of where the oxygen could have come from. Like I was saying earlier, all the carbon in this unknown compound had to go into the CO2. The only place this carbon in CO2 could have come from is that carbon there. The same thing is true of the hydrogen in water. It can only have one location that it could have come from, and that's the unknown compound. But with oxygen, we have a slight issue. The oxygen in both of these could have come from the unknown, or it could have come from the oxygen we're flowing through the system. And because of this, we can't determine how much oxygen was present from these two products because we don't know how much of the oxygen and CO2 came from our unknown or came from the oxygen we were passing through the container. The same thing is true for the oxygen and water. So we have to find another way of doing this. The answer to how we can figure out how much oxygen was present in the unknown actually comes from the mass of the unknown. Because if I have this mass of unknown, I know that that mass is equal to the grams of hydrogen plus the grams of carbon plus the grams of oxygen. And I can determine the grams of carbon and hydrogen. And if I know the mass of the unknown, I can back calculate how many grams of oxygen were originally present in the unknown. We're going to do this in an example problem in just a second. So again, just kind of saying, you know, the oxygen in the CO2 came from both the oxygen, the O2 gas that we're running through the sample, and from the unknown compound. So it becomes impossible to determine how much oxygen came from the sample from the CO2 and H2O that we produced. We have to do it in a different way, like I was just describing. So this is a bit of a review slide, just to kind of throw it in there. We know that an empirical formula is equal to the molecular formula if we multiply it by n, which is some integer value. N we calculate by taking the molecular formula's molar mass and dividing by the empirical formula's molar mass. And if I know this n value, I can throw it in there. If I know the empirical formula and the n value, I can get the molecular formula. So again, this is a review slide. We covered this in the last lecture video, or sorry, 2 lecture videos back, just to kind of remind you, because we're going to do it again in our combustion chemical analysis in a second. All right, so here's my problem. I have 1.516 grams of this unknown compound that is going to contain carbon, hydrogen, oxygen. After I subject it to combustion analysis, I form 2.082 grams of CO2 and 1.705 grams of water. Now, I'm also told that the molar mass of the compound is 160.2 grams per mole. First, my question is, what's the empirical formula? And then after that, I want to know what the molecular formula is. So the first thing I need to do is I need to calculate how many moles of carbon were originally present in my unknown compound from the mass of CO2. So I know I have 2.082 grams of CO2, and I need to calculate the molar mass of CO2. The molar mass of CO2 is 44.01 grams of CO2 per 1 mole of CO2. Next, I need to go from moles of CO2 to moles of carbon like we did in an earlier lecture video. We have to create a mole-to-mole ratio of carbon to CO2. I know that 1 mole of CO2 contains 1 mole of carbon. And I want to hit equals here and calculate this value. I get that the moles of carbon in the compound, I'm going to use a different color here because we're going to need this value later, 0.04731 moles of carbon. All right, so now let's do this again, but now we're going to do it for the water. 1.705 grams of H2O were present. We know the molar mass of H2O, or we can calculate it, is 18.02 grams of H2O per 1 mole of H2O. And I know that 1 mole of H2O contains 2 moles of hydrogen. Again, the goal here is to determine the number of moles of hydrogen present in my original compound. And by doing this out, hopefully you can see that moles cancel with moles of that, and grams cancel here. The same thing was true of our moles of CO2, grams of CO2, and all that up there. Okay, so let's calculate this out. you should get that there's about 0.1892 moles of hydrogen in the original compound. Okay, so the next step here is to take these mole values that we calculated and get how many grams of them are present so that we can back calculate how many grams of oxygen was in the original compound. So I know that 0.04731 moles of carbon is that, and I know if I multiply this by the molar mass of carbon, I can get the grams of carbon. Okay, so if you do that calculation out, you get about 0.5682 grams of carbon present in the original compound. Now, I need to do this again, but with the hydrogen. So 0.1892 moles of hydrogen times the molar mass of 1 mole of hydrogen is 1.01 grams of hydrogen. If I calculate this out, I get 0.1911 grams of hydrogen. Okay, all of this was in order to get the mass of oxygen present in this unknown compound. Now, by taking these two values here and subtracting from the total mass of the unknown, which is 1.516 grams, I can get what's left because I'm basically subtracting out the carbon and the hydrogen, and what is left is just going to be the oxygen present in the compound. So 1.516 grams minus 0.5682 grams of carbon minus 0.1911 grams of hydrogen gives me what's left, which is my grams of oxygen. And this gives me that there are about 0.7567 grams of O. And like always when we're determining the empirical formula, we need moles of each element. So I need to convert this from grams to moles. I know that the molar mass of oxygen is 16.00 grams per 1 mole, and I can calculate that molar mass. If I calculate the moles of oxygen, I get 0.0472 or 72 moles-ish. 73 technically. 0.0473 moles of oxygen. Now I used green again because now that I have all the mole values, right? I have the mole value, that's a bad color. I have the mole value here, I have the mole value here, I have the mole value here. I can actually determine finally my empirical formula. So let's do that. We have carbon is 0.04731, hydrogen is 0.1892, oxygen is 0.0473. And so we're going to divide by the lowest number, which is technically oxygen. So 0.0473, dividing all these guys out by that value. And this will get me, hopefully, my empirical formula. All right, so if we divide all those out, we get basically carbon 1, hydrogen 4, O1. And this is our empirical formula. All right, so I'm just going to kind of give us a couple seconds to look at all this work. This was a lot of work to just get the first answer, and then I'm going to erase everything. So this is our empirical formula, and we're going to need that for the next step. Okay, cool. Let's erase, and we'll do the last question here. Okay, so now that we just have our empirical formula, now let's calculate the molecular formula. We know that N is equal to the molar mass of the molecular formula, i.e., 160.2 grams per mole, divided by the molar mass of this empirical formula here. So let's calculate that value and then divide this out to get what N is. So if you calculate the molar mass of this empirical formula, you should get 32.05 grams per mole. And we just put that down here in our denominator. And we should be able to get our N value. This gives us, again, pretty much exactly 5. So my last step here is to take my empirical formula, C1H4O1, and multiply the whole thing by 5. This will get me my molecular formula, which should be C5H20O5. And this is my final answer for the second problem here. All right, so this is about as hard of a problem as it gets for chapter 3. And with this, we're now done with all the material for exam 1. As always, please, please, please come talk to me if you have any questions.